So I'm representing PicoQuant, and PicoQuant just celebrated its 25th anniversary, and we are, let's say, market leader for photon counting instrumentation, which in particular is used and which I will focus on in lifetime imaging and also single molecule quantification. So PicoQuant is, reconnect. Let's see. Come on. Sorry. Oh, we are there. Oh, yeah. Okay, good. PicoQuant is located in Berlin, so capital city of Germany, and but not in the city center. We are rather in the east, southeast located, and yeah, now we are producing and developing pulse diode lasers, time-resolved confocal microscopes, and the LSM upgrade kits, as well as fluorescence lifetime spectrometers and the photon counting instrumentation. So basically, everything what is required for photon counting measurements, yeah, and lifetime imaging is directly produced through one company. We were founded in 1996, and now we're going to have more than 100 employees. Background of most of the people in the team are electrical engineers for lasers, physics, and chemistry. This is like the background of our people, but also the biology people, like I am, are important because we're going to know the application of also most of the life scientists and also the core facility guys. So besides that, we also established in April 2008 PicoQuant North America, and we are dedicated to optoelectronic research and development. So this is like a schematic or a pictogram overview of our key expertise and also the applications which are possible. On the one side, we're going to have the pulse laser diodes and LEDs. We do have the photon counting and also the single photon counting detectors, which we developed by ourselves. Fluorescence spectrometers for cuvette experiments, and the fluorescence microscope. And this can be used for life science, material science, meteorology, so LIDAR experiments, or quantum optics, which is now also a key field. So just very briefly, rushing through the portfolio of PicoQuant, we do provide the systems for characterization analytics from, let's say, maximum flexibility, like 2 monochromators for the emission and excitation range in the IR, NIR detector, visible detector. This is all possible, but we can also go and move a little bit smaller, more compact for the cuvette experiments with our fluid time 250, and both are lifetime spectrometers. Yeah, so this gives you always the additional information beside the intensity information. On top of it, we're going to have also microscopes which are, let's say, optimized for material science or anti-bunching, carrier diffusion, so everything regarding LED, LCD development, semiconductors. And then we're going to have 2 variants, one with a confocal resolution, which is the microtime 100, or our newest member is the FluoMIC, which basically combines wide field imaging with a spectrometer. So you can have a look at emission. Yeah, you can do like an emission spectral scan and get the lifetime information on top, for example. And for the life science community, we do have also two systems. One is basically an upgrade kit that you can attach to every laser scanning confocal from Nikon, Olympus, Scientific, or Zeiss, or let's say to most of them. And this enables then the microscope to perform lifetime imaging and also FCS measurements. Our other, let's say, member is the Microtime 200, which is our own confocal microscope, our in-house built confocal microscope. And this is, let's say, a single molecule platform. Yeah, so this is optimized for highest sensitivity to really perform single molecule experiments. And just like to show you one example that PicoQuant just built up extremely robust systems is that very recently our Microtime number 6, which is like which was installed in 2004, just generated a new high impact publication at Scientific Reports, where FLIM FRAD measurements was combined with a home-built stat upgrade. And so, yeah, valuable publications after 15 years are no problem. And I personally did my PhD on the first ever installed LSM upgrade kit on a FluoView 1000. And all the systems are based on our own development for the of the pulse lasers, detectors, and the photon counting instrumentations. Now let's come like say, more to the application side, and what kind of information does actually give you the lifetime information. And on all confocal microscopes, you do have the readout for the intensity. You also can do, let's say, a spectral emission scan. And yeah, polarization is already difficult. But what the lifetime information gives you is basically the time that the fluorophore occurs in the excited state. And how are we going to measure that? So we're going to have a pulse laser, and we're going to excite the fluorophore. And then we're going to have a stopwatch, a start-stopwatch, and a single photon counting detector. And we press start when the laser was turned on, and we press stop when the photon arrived at the detector. And this photo cycle takes around like picosecond to the nanosecond range. And here's like a little video cartoon. So we're going to have the laser. This fires photons. And then the sample gets excited, and sometimes the detector detects a photon, sometimes not. And this we're going to do in a repetitive manner. And by that, we simply build up a histogram. Yeah, there also might happen that during one laser shot, no photon was excited at all. Yeah, so after many cycles, we're going to have finally our histogram. And by using this histogram and taking this lifetime information, we do get a new dimension. And this allows us, for example, to identify fluorophores just on top of the excitation wavelength. You do have then lifetime information. You can remove the background using time gating. You can also just use it as an additional contrast parameter. Yeah, using one laser excitation, and you get like suddenly a colorful image just by using the lifetime information, which is shown there on the right side. You can differentiate different tissue types, because also tissue types do have a different autofluorescence lifetime. And you can also, of course, use it to perform quantitative measurements. For example, protein-protein interaction. FLIM-FRAT is like the mostly known application for lifetime measurements. And you can also use it in material science. And this is the example where FLIM, for example, just gives you an additional parameter, additional contrast. Now, left side, excitation 485 nanometer, emission bandpass was used at 520. And this is the simple grayscale image. But when you add the lifetime color coding on top, you then see that in this daisy plone, you see then suddenly some contrast, which was not there before. And you can use the average lifetime, or you can perform lifetime fitting. And you can also use the lifetime just to simply select the region of interest, like also shown here. Yeah, so we do have different lifetimes at the rim and in the center. And just like this, on the right side there, histogram, you can select the region of interest based on the shorter lifetime. But before, let's say, these lifetime measurements, they took rather long. 1 minute or longer was normal. But back in 2016, PicoQuant develops the first rapid FLIM electronics. And this had at that time a rather low temporal resolution, 250 picoseconds, but the dead time was already very short. And the dead time, I will show you the effect of the dead time the next slide. But PicoQuant continuously improved the electronics. In 2018, we were able to get down to 80 picoseconds, and the dead time was at 0.6 nanoseconds. 2020, even we could launch rapid FLIM high resolution with 10 picoseconds temporal resolution, and now we are at 5. And the number of detection channels increased up to 64, which also is, for example, important for quantum-like measurements. And of course, like this needs some additional mathematics, and this was like developed in 2017 from us. So what you see here on the right side is simply that the lifetime image and a Z stack takes like a minute for 30 frames. And nowadays, it's simply the scanner speed is the limit. So, and what happens, classical TC-SPC, you simply do lose photons, because of the dead time. The electronics is simply blind due to computational time for detecting or calculating photons within the same laser pulse, or even the next or the afterwards laser pulse. But now with this very, very short dead time, we can simply detect every single photon, and even 2 photons within one laser pulse is also no problem. And this is like the history of some electronic parts. So we started with a PicoHub 300, which has a very good time resolution, but a very long dead time. And in 2016, we developed the TimeHub 260 nano. Short dead time, 2.5 nanoseconds, but high temporal resolution. And now you see that this slide is even not yet, let's say, the current state, because our multi-harp has got now 5 picoseconds and 0.6 nanoseconds that time. And this allows you then to observe a complete new, let's say, range of possibilities and perform different types of measurements. here you see GUVs, and GUVs, they are normally floating around in solution. And with a classical FLIM, you would only get this blurry image, but now you can achieve enough photons in a short time scale to perform really high resolution lifetime images. And you can also visualize dynamic processes. And like here, for example, membrane tension measurements. Here we performed an hyperosmotic shock and afterwards a hyperosmotic shock. And the lifetime changes were like simply done in a second or two. And even this fast changes we are now able to observe. And this you can use because of the high temporal resolution of our electronics also to measure and perform calibration measurements. Yeah? Out of the lifetime, you can then get the information of the osmolarity. You can also get the information based on the same fluorophore or same sample, let's say. Here, the group, they had a pull experiment on a cell like structure or on a GUV, and they just like added some force to pull some membrane right out of this GUV. And at the end, based on the lifetime, you could calculate the forces which were applied, yeah, and the millinewton range. And then you simply see that these were like depending on the composition of the lipid of the membrane. And this then at the end, yeah, led to a full range of publications. But it's, and here's another like straightforward example for calcium imaging. And also here we are able like now really to measure calcium changes based on the lifetime information. And we are also even able, we are not only able to measure the baseline and the peak, we can also even measure the lifetime in between, in this rising flank of the lifetime. But like this is let's say one timeline of the developments, the developmental milestones of PicoQuant. And you see that basically we are continuously improving our technology and yeah, really going to the edge what is possible. But it's not only technology that we do produce and offer, it's also our scientific contribution. Back in 1996, we organized already the second international workshop for single molecule spectroscopy in life science. And then in 2003, we had the first European short course of the principles of applications of time-resolved spectroscopy, and our TRF course. And in 2008, we had the first time-resolved microscopy course, our thermic course. And also these are like also anniversary now. Yes, the single molecule workshop got like 25th on last year. And also, I think now 3 years ago, we had our first international symposium for single quantum-based technology. And so also we're going to that direction now. And with this, I would like to thank you for your attention. I hope you do not fall into sleep like this little fellow. And now I'm very happy to answer questions. Thank you.